Okay, we have a quiz coming up in 3 weeks. Okay, the first quiz is basic quiz. Let's hand those in at the end of class now. Could everybody just take their seats, please? The quiz is coming up in 3 weeks. The first quiz is essentially a mastery quiz. Do you understand the basic material? The way I like to think of it is this is the quiz that separates the C's from the F's. In other words, tells people whether they should drop now. I usually don't like it when people who fail quiz 1 continue with the course, because usually they end up failing the course and they've just invested all that time in an enterprise when they, could have been doing other things with their lives that would be more productive. Okay? So this is a quiz that's basic mastery, so cleverness is not as important on this first quiz as just basic mastery of material. On quiz 2, that's where cleverness is way important. Okay? But quiz 1 is basic mastery of material. Okay, we have a lot of stuff to cover today. Today is a hard lecture. It's one of the hardest we're going to do in terms of mathematics. And it is one of the fastest we're going to do. Okay, it's one algorithm we're going to study. It's called quicksort. Yeah, could you folks take your seats and do that after class? Thanks. Okay. It's called quicksort, and it was invented by C.A.R. Hoare in 1962. So this is when I was 9 years old. Okay, so this is an old algorithm. Okay, it's a divide and conquer algorithm. Okay. So we'll see what the structure of it is. It's actually a very tricky divide and conquer algorithm. That's one reason we cover it, because you're not going to, in general, have to do anything this clever in terms of analysis. But by taking you through the analysis for things that are hard, you discover that you've got a greater facility for doing the common things that occur, because the common ones don't seem nearly so hard if you've seen that, hey, it could get a lot hairier. This is an algorithm that sorts in place. And by that we mean that it rearranges the input in place rather than making the output be a copy of the input but permuted. So it rearranges it in place. What's the advantage of sorting in place? Yeah, it can use less memory typically. So if you're memory constrained for what you're trying to do, okay, you can do a bigger sorting problem if it's in place. Okay? And yeah, we've seen two other algorithms, insertion sort and merge sort. Are either of those in place? Somebody over in that back corner? Are either merge sort or insertion sort in place algorithms? There are only 4 people back in the back corner there. Well, we could take 6 or 7 if we wanted to. I want to get the people in the back corners to interact. So is insertion sort in place? How about you?
No.
Excuse me?
No.
Well, I had a 50% chance. Okay, and actually we're going to look at randomized quicksort, so we'll do probability, but turns out you're unlucky today. Okay, answer is yes. Insertion sort just rearranges things in place. Okay, what about merge sort? Once again, 50% shot. Okay, no, why not? Yeah, because basically to do the merge, nobody has come up with an algorithm that can do the merge in linear time with just rearranging them in place. You sort of have to make a copy of the output, because otherwise there's no place to put it. So the merge operation in merge sort doesn't allow it to be in place. So this is like insertion sort, but not like merge sort. And it's also very practical. Okay? And it usually is especially practical if you do some code tuning. Okay, meaning you tweak up the constants and you handle special cases, and there's all kinds of games that you can play to make this an even more efficient algorithm than what the basic code is that we'll look at today. So let's see how this algorithm goes. We're going to go really fast today because there's just a lot to cover. Okay, so it's a divide and conquer algorithm, and the first step is the divide step. And the basics of quicksort is sort of the opposite of merge sort in some sense. In merge sort, the divide is very simple. We just do an index calculation to find the middle element. Okay, I mean that's or to divide, it's all implicit, so it's trivial. And then we recursively sort the two subarrays, and then we merge them. This one's the other way around. We start out by partitioning the array around what we call a pivot element. So we partition the array into two subarrays. Around a pivot x, such that the elements in the lower part of the subarray are less than or equal to x, and those in the upper part of the subarray are greater than or equal to x. So the partition step yields an array. We'll look at the array like this, where x falls somewhere, and the elements to the left of it, in the lower part, are less than or equal to x, and the elements here are greater than or equal to x. And that's what the partition subroutine does. And we'll talk about how we implement the partition subroutine in just a moment. Okay, but I'm giving sort of a top-down description of the algorithm. Okay? So step 2 is to conquer by recursively sorting the two subarrays. Okay, so we sort everything in this subarray, and we sort everything in this subarray. Okay, and what's left to do to get the sorted answer for the combination? What's left to be done? Excuse me? Eliminate the pivot? No, because the pivot you want to have isn't going to be an element in the subarray, so it wants to be there. Okay? Nothing. Okay, we're done. Okay, combined step is trivial. Okay? So once we've sorted these and sorted these, the whole array is sorted. Okay? Nothing needs to be done. So the key for this, for the efficiency of quicksort is that this partitioning can be done very efficiently. Okay? And in particular, it can be done in linear time. Okay, and that's what we're going to look at next. Okay, so linear time meaning it runs in order n time, where n is the number of elements in that you're partitioning. Okay, so that's what we mean by linear time, order n. Okay, so so the code in the book. So I took the drastic step of rewriting the code in the book. Okay, whenever I do this, I usually make a mistake. But I think that what I came up with is simpler than what's in the book. So I'm going to give you what the new code is. That'll be in the next edition, okay, if it's right. Or else one of you will pick out the bug in it, and then we'll see what the problem is. In any case, there are a bunch of different ways of partitioning. So I think that this one is easier because it's got a little bit easier index calculations. So So I call it partition of A, P, Q. And it's basically working on the subarray A from P up to Q. Okay, so it's taking that piece of the subarray and it's going to partition it. And the first thing it does is it uses the first element, A of P, of the array as the pivot. Just takes the first element and says, that's my pivot. Okay, now, the version in the book takes the last element and it uses the pivot. Okay? I don't care which partitioning algorithm you use generally for the things you're doing. It doesn't really matter. Okay, there's actually Hoare's original partitioning algorithm also uses the first element, but it's a completely different partitioning algorithm from the one that I'm presenting, which is very similar to the one that's in the book. Okay, so there are several that have been proposed for various reasons. Hoare's is probably the best to use in practice. Okay, whereas this one is actually easier to understand what's going on, and it's a little bit simpler to describe. Okay, so here's the code, and then we'll discuss what it does. So let me just write it up. Oh, and for those people who asked for the lecture notes to be available before class, they were. Unfortunately, Media 1 was not giving me a good time last night, so I couldn't upload them from my home last night. I tried again this morning. I couldn't do that, so it wasn't until I got into work that I was able to upload them. So people who wanted to take notes, I only finished them late last night, so I was hoping to upload them from home, and I was unable. Okay, but I will try to have notes done online before class, and hopefully somewhat before class, as opposed to immediately before. Okay, so this is the code. How do we know what this thing does? What's the easiest thing I can do to show what this code does? How can I help you understand this? How can you understand anything with a loop? Give the invariant. Loop invariant. If you know the loop invariant, it's easy to understand things. If you don't know the loop invariant, what's it doing? I don't know. Okay? In documentation, when you write code, very good idea. Put loop invariants for the loops that you write. Okay? It will help other people reading your code to know what's going on. So the invariant for this, I'm going to do in picture form. Okay? Because that's the easiest way to understand it. Here's the array. The invariant in the loop is that, well, x is in the position A of P. And at any point, we have three parts of the array, some of which may be empty, especially at the beginning. We have a point that ends at I, we have a point that begins at J and ends at Q. And we have the parts that are between I and J. And the invariant is that everything here is less than or equal to x, everything here is greater than or equal to x, and these are the things we don't know about. Okay? So essentially, let's take a look. So I and J, I initially starts out as P. Okay, so this thing is empty. And J starts out at P plus 1. So this thing is empty. And so it's just X, and everything is a question mark. Okay? And at each step, what we do is we increment J. And then what we do is we first check if is J less than or equal to X. Okay? Well, if J is greater than X, how can I maintain the invariant? Just increase J. Right? Because if this next element here is greater than or equal to X, there's nothing to be done except to increase J, and the invariant is satisfied. Okay? However, if this element here is less than or equal to x, okay, then I've got a problem because my invariant isn't satisfied. The way I fix the invariant is I increase I, and I swap this element with the new value for a of I, thereby making it so this thing is now less than or equal to x, and the value that was here is now greater than or equal to x. And now I can increase j. So that moves up. Okay, we'll do it on an example. Okay? So the tricky thing is what happens when it's less than or equal to x, okay, less than or equal to the pivot. And then the point is that we can still maintain the invariant by swapping two elements, and now we can increment both. Okay? So how much time, before we go into the example, how much time does this algorithm take on n elements? Somebody from that back corner. Yeah. Linear time, right. Okay, it's theta n for an n element subarray. Okay? Because all it is a for loop. And that what's going on inside is constant time, and it's constant time outside. Okay, so it's actually taking what, q minus p steps, and if that's the number of elements, how many elements are in there, that's proportional to n. Okay? Let's do a quick example. And we'll see how this goes for so suppose I have 6, 10, 13, 5, 8, 3, 2, 11. So the first thing that I do is I set my pivot. So x is going to get what? 6. As I mentioned, in the one in the book, it uses 11. Okay? Similar algorithm, just it's a different partitioning algorithm. So that's the pivot. Okay? And I starts out here at p, and j starts out at p plus 1. Okay? And what j does is it looks. It says, is this is this less than or equal to 6? No. So then it just increases j. And checks this one. Is this less than or equal to 6? No. So it increases j again. Then it comes across this guy, which is less than or equal to 6. Now something needs to be done. So at this point, we've essentially established this region here as being the part that's greater than or equal to x, and we suddenly hit something that doesn't let us extend our invariant by simply increasing j. Okay? So what we do then is we look at this value, and we increase I and look at this value. And we swap them. Okay? And when we do that, we get 6. Okay? 5 and 10 are swapped. And the rest of the array is the same. Okay? And now I is moved from here to here. And j starts out getting incremented as well, starts out here. And we compare with this one. Okay? And once again, this is the part now here which is greater than or equal. We go one step and we discover something that's less than or equal. Okay? So now what we do is we swap this one with which one? 13. Okay? So we get 6, 5, 3, 10, 8, 13, 2, 11. Okay? And I now is increased to here, so that my two pieces of the subarray at this point are this, and j gets increased to over here, and this. Okay, so you see everything here is less than or equal, everything here is greater than or equal. And now we look at 2, and that's less than or equal again, so we've got to do another swap. Okay, we swap 2 with 10. Okay, so we get 6, 5, 3, 2, 8, 13, 10, 11. And j gets increased to here, and I gets increased to here. So here are now my two pieces of the subarray. Okay? And now we increase j. We go off the end, so the for loop terminates. Okay? And so this gets extended. Okay? 11. And so now I've satisfied the first part that that's what the structure is. But now I want to put this element where it belongs. Okay? And so the way that I do that is I simply swap it with the last element of the first subarray. Okay? So basically I then get 2. So this I swap now with this. Okay, that's these last two lines. Or sorry, this last room line. This is, by the way, an I, not a 1. Okay. So this gets 2, 5, 3, 6, 8, 13, 10, 11. And this is one subarray that needs to be sorted. This is another subarray that needs to be sorted. And this is the pivot right here. Okay, so we sort of go through and we maintain this property, this invariant, so that by the time we're done, we've partitioned the elements. Now, in principle, partitioning is not very hard. You don't need to know this algorithm to partition. What do? You take an element, you go through all the elements, and you sort of sort them into 2 bins. That's how you partition things, right? You don't need a fancy piece of code like this, okay, to do that. But what's nice about this is it does it in place. Okay, and it's a very efficient piece of code. It's a very tight loop. Okay, and so it makes it so that the algorithm is not just theoretically efficient, it's practically efficient. Okay. Okay, any question about the partitioning algorithm? Okay, let's give the actual code for quicksort. Pseudocode, that is. Got a lot to do today. So here's the code. It's pretty simple once you have the partitioning algorithm. A of P and Q. It basically goes like this. So if we're quick sorting a subarray A from P to Q, okay, we look to see whether the subarray has more than one element in it. Because if it's only got one element, there's nothing to do. So the termination condition of this code is you do this check. And if P equals Q, or it's a 0-element subarray, in which case Q would be less than P, okay, nothing to be done. Okay? But if there is something to be done, then we partition the array A from P to Q, the subarray, and we return the index of what the partitioning element is. And then we recursively sort the first subarray and the second subarray. Okay, pretty straightforward code. So the initial call for a whole array is to quicksort A1 to n. Okay, and I've just given the recursive part of the algorithm. Okay, you sort the whole array. Okay, if A is a whole array. Okay, any questions about? So that's quicksort. Okay, most of quicksort is either if you decide you're going to tune this code so it really goes fast, okay, or you want to analyze it because it's not exactly clear how well it behaves. And that's what we're going to spend the rest of the lecture on, is understanding some aspects of how it behaves. So any bug in this code, by the way? Anybody notice a bug? Okay, if there is, let me know. Okay, so the analysis, the basic principle of the analysis that is going to be used in quicksort. And it's actually an unfortunate assumption to have to make for quicksort, because quicksort is a great piece of a great sorting algorithm, but it's one of the reasons that this partitioning algorithm is not used in practice. And that is that we're going to assume that all elements are distinct. In other words, you don't have any duplicates. Now, in Hoare's original partitioning algorithm, it actually, if there are duplicates in the array, it works better than this code. What does this code do if all, for example, suppose that the array is just filled with 97s? What does this partition algorithm do? Yeah?
It swaps it every single time we have something aj equals x, we could just have in the...
But what's the result? Not what does it do at every step. What's the result?
The result just leaves it at the same. It does a lot of work on swapping from 7 to...
Yeah, the swapping I'm not so worried about at this point. Yeah? Yeah, one of the subarrays ends up having no elements in it. So when we're doing the divide and conquer, we do all this work, and all we do is pick out one element. It's not a very effective partitioner. It doesn't sort of, we're going to discover that it's really helpful if you can divide it in the middle. Okay? And if they're all the same, then it doesn't divide in the middle. And that's one reason that Hoare's original algorithm is a better algorithm if there are duplicates. Okay? But we're going to assume for now that all elements are distinct. Okay? Because that's the cases where they're not all distinct, you have to use a somewhat more complicated algorithm in order to get the properties that we're going to talk about. But if they're all distinct, then the analysis is easier. So we'll let T of n be the worst case time on n elements. Okay? And when does the worst case occur for quicksort? I run this algorithm. When's the worst case going to be? If it's already sorted. Why? What happens when it's already sorted? It picks out the first element, and then it recurses on no elements on one side and n minus 1 elements on the other side. So the split is sort of a 0 to n minus 1 split. Okay? And then it does that every subsequent step. Okay? What's another worst case for this? Yeah. Reverse sorted. Same thing. Now it does a partition on the largest element every time. Okay? So the worst case is either the input is sorted or reverse sorted. And so one side of the partition, there's one subarray, has no elements. So let's analyze that case first, because that's the easiest one to analyze, the worst case. Okay? So we get a recurrence in the worst case. So we can write the recurrence basically by looking at the divide and conquer. The time on n elements in the worst case is going to be the time, well, if we have 0 elements on one side and n minus 1 on the other, the recursive calls are going to cost us t of 0 on one side plus t of n minus 1 on the other side, plus the amount of time that we spend partitioning and the other minuscule stuff like the comparison of p to q. And how much time is that here? Theta n for n elements. Okay, so we can get this recurrence. This term is what? We know what that is. What's this term? T of 0 is constant. Okay, it's theta 1. So I'm just going to drop it. Why can I just drop this? Because you can just absorb it into the theta n here. Okay? In other words, it'll be a different function here when I drop it. The different function hidden over by the theta n. Remember, theta n is a set of functions. And there's some particular function that's there. Well, I'll pick a different particular function that bounds the original particular function here plus whatever the t of 0 is, which is a constant amount additional. Okay? So this is basically absorbed into the theta n. And so that's just equal to, okay, t of n is t of n minus 1 plus theta n. What's the solution of this recurrence? Okay, these now you can do in your heads, right? Theta of n squared. Why is that? Somebody justify that for me in two words? 2 words. Arithmetic series. Good. This is just like, what algorithm did we see that had this recurrence? The recurrence without this. We've only seen 2 previous algorithms, so 50-50 chance. Yeah. Insertion sort had exactly this behavior. So here we've done all of this work, right? And when we're done, we have something that's no better than insertion sort in the worst case. Moreover, how well does insertion sort work when the input is sorted? Somebody in the middle here. How well does insertion sort work when the input is already sorted? N elements. I want to sort with insertion sort. I see people staring off. They don't want to give me eye contact. Eye contact. Okay. So, you've answered already one. Got to have some people who haven't answered. How about the middle over here? Otherwise, I'll pick, and then if you... So my general rule when I pick people who don't raise their hand is you can either answer or you can ask a question. You got to do one or the other. It's got to be a pertinent question. Okay? Okay, so who's ready to answer a question here? Ask a question. Okay, so I'm going to pick somebody in this, right in this middle part here. Okay, so don't all grin at once. What is the running time of insertion sort when the input is already sorted? Very good. You're in the middle, too. Okay, it's order n. So here we've just come up with a more complicated algorithm that's got the same running time, and on a sorted array, it works badly. And in practice, often when you're sorting stuff, as we discussed on the first lecture, it's already sorted. Okay, checks tend to clear banks in sorted order. So what's good is this? Well, the answer is that it is actually a great algorithm because on average it works pretty well. Okay, so what I'm going to do is do a best case analysis. So I'm skipping over. Okay, to begin with, to get some intuition up. Okay, so let's see, where shall I do my best case analysis? Now, we talked about best case analysis a few lectures ago, right? And I had some pretty disparaging words to say about best case analysis. Okay, what did I say about best case analysis? Yeah, bogus. Okay, so this is something which is bogus. You don't do it. So why am I doing it? Okay, well, in this case, the reason I'm doing it is for intuition. We're not actually going to claim that this best case analysis tells us anything particular, because all it's doing is just sort of for one case. But what it's going to do is it's going to help us to develop our intuition for what's really going on in quicksort, okay, in the average case. And then we'll dive in and understand the average case. Okay? So this is what we're doing for intuition only. And it's always fine to do anything you want for intuition. Okay? It's just not fine to hand in a piece of paper and say, hey, best case analysis of this algorithm is. Okay? So what happens if we're really lucky when we're running this algorithm? If we're really, really lucky. Really lucky. Okay? What kind of split is partition going to give us, do you think? It's going to be the lucky, lucky, luckiest possible split. Yeah. Even. Right down the middle. Okay, that would be really lucky. Okay? So if we're really, 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 really lucky, oh, I need one more really in here. Really lucky, okay? Partition splits the array n over 2 to n over 2. Okay, and I'm not going to worry about floors and ceilings here because, as you know, we're allowed to be sloppy in this class as long as we know what we're doing. Not allowed to be sloppy if it would change the answers. Okay? So if that happens, what recurrence do I get for quicksort? The time on n elements is going to be what? Good. 2t of n over 2 plus theta n. Great. I got some people with me. Okay. Because I'm recursing on two subproblems of size n over 2. So I've got twice the work to solve the subproblems. Here's the two subproblems. Both of them have to be done. So it's 2n over 2. And then all the other work, partitioning and whatever, that's all order n. Okay? And what's the solution to this recurrence? Yeah, theta n log n. How do we know that? Yeah, either you remembered it from merge sort, this is the merge sort recurrence, or, more importantly, the master theorem. And which case is this of the master theorem? Case 2. Good. Okay, so this is case 2 of the master theorem. It's like merge sort. So that's pretty good. This says, hey, if we got good splits, we would be doing well. Suppose that we're not really, really lucky. We're just maybe lucky. Suppose that the split is always 1/10 to 9/10. Because it doesn't cut it in half, it only shaves off 10%. Okay, that's pretty much towards the outlying. That's almost like just cutting off 1. Okay, which is what happens in the worst case. Okay, but you're way off. Okay, what recurrence do we get? So how about somebody from the back middle over here? I'm going to pick on the people in the back. And this is a heuristic for seating. Okay, somebody in the middle and the back here, in the middle back here, about 4 or 5 rows in here. Who would like to give me the recurrence there? Okay.
Is it T of n equals T of n divided by 10?
Yeah, 1/10 n.
Plus T of
9/10 n. Plus theta n. And what case of the master theorem is this? Yeah, you need something like acrobacy, or master theorem doesn't apply here. Doesn't have the right form. Or you can, for things like this, actually even easier sometimes than memorizing acrobacy is just to solve it with substitution. Or what we're going to do is we're going to do a recursion tree which will give us the right guess, and then we'll be able to solve it with substitution. So let's do a recursion tree for this. Actually, first, I'm going to simplify the recurrence a little bit. I'm going to just say that's less than or equal to some Cn, and that way I won't have thetas showing up in my recurrence. Okay, I could say that it's some h of n, where h of n is order n, but it's easier if I just put the bound of Cn in it to see what's going on. Now, recursion trees, as the Singaporean students will know, I don't ever believe in drawing recursion trees by drawing the full drawn-out recursion tree at the beginning. That's a guaranteed way, especially if you're new to drawing recursion trees, to make a mistake. The way you should do it is do it iteratively. So you start with a recursion tree that consists simply of the running time, t of n. And then we rewrite the recurrence in a tree-like form, putting this thing at the root. Okay, so that basically gives us Cn And then plus we have to add in t of 1/10 n and t of 9/10 n. And the invariant that I'm going to maintain from one step of the development of the recursion tree to the next is that the sum of everything in the recursion tree is always t of n. Certainly true here, and it's true here, because that's what my recurrence says. Okay? So the next step, I simply use this formula to expand each of these at the next level. So I get Cn, that didn't change. And now when I expand t of 1/10 n, what value do I get here? How about somebody on the aisle seats? The aisle seats are prime seats, I can tell. Everybody's got aisle seats who can get one. So somebody down this aisle answer this is actually a good scheme. Okay, I know that the person 6 down isn't going to answer. Okay, but somebody else, tell me what happens here. What value do I put here? What happens when I expand t of 1/10 n? I plug 1/10 in here. What value do I get at the root? So this is the thing that goes at the root. So this is the left subtree. This is the right subtree. And this is the root. So what value goes at the root of this subtree then? Somebody in this thing. Yeah.
Cn divided by 10.
Yeah, Cn divided by 10, or 1/10 Cn. And what about here? Actually, let me expand this fully. This is actually the right thing to do. And then what do I get here? T of 100th n. And here? 9/100ths. Okay? And now we do this one. What do I get over here? How about somebody in this aisle besides you? But you've answered before. You answer too much. Okay? So do you. But the other people don't answer so much. 9/10 Cn. Good. 9/10 Cn. Okay. And then what do I get here? How about somebody on the far aisle over there? Okay, I'm plugging 9. I'm plugging 9/10 n in for n here. So in the left subtree here, I get 9/10 n plugged in here. What do I get? Somebody in the far aisle there. Somebody raise your hand so I can pick. Yeah, go ahead. Good. 9/100ths n. Same as I got here. Right? And then here I get what? 81/100ths. Okay, times n. Okay? And I keep doing this over and over. So if you try to just write down the last step, you're likely to make a mistake. This way, I very much believe students, one of the biggest mistakes students make is they don't put enough of the right stuff down so they can check their work. They think they're saving time by not writing it down. And what they do is they make it so that when they have an error, they can't find where the error is, and they spend all their time trying to figure out where their error is, rather than just being very careful and methodical and writing things down and recording something so that you can go back and check and say, oh, yes, I see what happened there. So they tend to do things like skip 3 steps in the conversion of an equation, rather than doing each equation step by step. So they can go back and check, oh, I see where I made my error. Okay, instead, every time they go back to check it, they have to recalculate. Okay? So anyway, here, the last step, oh yeah, we've got to do equals and our infamous ... which is why this is not a very rigorous method. This is really best for getting a good guess to use in the substitution method. So we get Cn 1/10 Cn 9/10 Cn and 1/100th Cn 9/100ths Cn. Okay. 9/100ths Cn, 81 100ths Cn. Okay? And we keep this going on till we get down to something of size theta 1. And we keep this going down until we get something of size theta 1. Okay? Actually, I'm going to redraw this just a little bit because I don't want to give the impression that these two things are at the same height. They're not. In fact, if I go along the left spine here, notice I'm going to get to theta 1 quicker than if I go this way. Okay? So let's do a little bit of adding, and then we'll look more carefully. So in the recursion tree method, I then add across this way. Okay? So this represents, okay, this is equal to everything that was over here. Okay? It's equal to the same thing, which is t of n. That's my invariant. Okay? So if I add up everything in this tree, I'm going to get what t of n is. So I add up across this way, and I get Cn for the first level. What do I get for the second level? Cn. What do I get for the third level? Anybody care to guess what I get for each of the levels in the dot, dot, dot? Cn. Okay, good. Okay. Now, the trick here is, how many levels do I have to go? Well, which path in this tree is the longest path? The far right, the right spine. The one that goes from here to here. And the height of this is what? The length of this. How many times do I have to 9/10ths something before it gets to 1? So if I have to have it, that's log base 2. If I 9/10ths it, that's log base 10/9. Okay? Log base 10 over 9 of n. Okay? So therefore, t of n, if I add all this up, total, okay, I'm going to write it over here, t of n is going to be less than or equal to the height times every level has Cn. Okay, so I get Cn log base 10/9 of n, plus I have a bunch of theta 1s floating around here near the bottom. Okay, and the number of those is going to be bounded by the number of leaves. How many leaves do I have? Another person. Okay, how many leaves do I have? How about shallow middle here? Shallow middle. I saw your eyes open up. O of n. Good. Why is it O of n? Good. The number of elements in the array. Because every time you're dividing it, remember, you're moving one element. And so as you divide up the tree in the recursion of quicksort, you keep going down until you get to one element, okay, or 0 elements. But the point is there's only order n of those. Okay? So therefore, I have an extra term, order n here, that I might have to add in, but that's going to be dominated by the Cn log n. So I get this is n log n. Hey, that's great. Order n log n. Okay? Okay? We can actually do a lower bound, too, by looking at the other side here. Okay, what's the height of this? Okay, or the length of this? Log base 10 of n. Good. And so actually on the lower bound here, I have Cn log base 10 of n. Well, once again, log base 10 versus they only differ by a constant, right? Log base 10 and log base 10/9 and log base any constant only differ by a constant, right? That's one of the fundamental properties of logarithms, right? Okay? So in fact, this is theta of n log n in the worst case. It's in this case. It's theta n log n. Okay, and that's lucky. Okay, we're lucky here. Lucky. Lucky. That was good. Even if when we just cut off a tenth. Okay, so let's just think about this a second. What if it were 1/100ths and 99/100ths? What's the solution going to be? Is it going to be lucky or unlucky? Lucky. As long as I'm cutting off a constant fraction, even if it's by just a little bit, if I've got a constant fraction, the solution is n log n. Okay? So that's a really important thing to understand about the recurrences. Now, of course, the constant that's being hidden here gets bigger. So as a practical matter, once I start shaving off just, 1 in a million, yeah, that may work, but the size of input I need for that to dominate some other algorithm may be big enough not to make that worth my considering in the engineering. Okay, but theoretically, there is nevertheless an n out there such that eventually something that shaves off 1/1,000,000th every time, okay, is better. And that's better than shaving off 1/nth every time, which is what the worst case algorithm does. Okay, the worst case algorithm shaves off 1/nth. Okay, so 1/nth is like tiny. Okay, it's smaller than a constant fraction every time. But if you can get up to a constant fraction, that's good. How are we doing on time? We are cooking here. I've already left some stuff out, by the way. You're pleased to know. Okay. Suppose that we alternate a lucky, there's 1/10 n/10 split, with an unlucky split. Suppose the algorithm goes and the first time it splits, it's lucky. At the next level, it's unlucky. Gets the worst case one. Then it's lucky at the next level, then unlucky. Then lucky, unlucky. All the way down. In the end, for the total algorithm, okay, we've got an equal number of luckies and unluckies. Which is better? Is the overall algorithm lucky or unlucky? How many people vote the overall algorithm is lucky? Oh, that's quite a few people. And how many people vote that the overall algorithm is unlucky? Okay, good, good. We got a minority viewpoint here. Okay. So let's analyze that. I'll tell you, for all of you who have intuition, one of the things that I love about mathematics is that my intuition is so bad, okay, that math always gets me back on the right track. Okay, it's one reason I love math. Okay, so suppose we alternate. In fact, when I'm surprised, that's usually when I know I'm doing good research. I say, oh, is that really true? Wow, I wouldn't have thought that. Okay. Okay, so we can write a recurrence. The lucky levels, lucky of n, is twice the cost of doing unlucky at n over 2, plus theta of n. So this is a lucky level. And then, at an unlucky level, okay, we end up with getting a lucky at the next level of n minus 1 plus theta of n. So this is the unlucky level. So here we have coupled recurrences. Okay? So we do lucky. If we do lucky, we get to split it into two problems, but each of those problems is going to be an unlucky problem. If we do an unlucky split, well, we get this 0 to n minus 1 split. Okay? But then at least we're solving the next problem with a lucky one. So who wins out here? Okay? So we can solve this by just substituting the un here in here. Okay? So L of n then is equal to 2, and now we do our substitution, which is L of, and now I put n over 2 in here, so I have n over 2 here, n over 2 minus 1, okay, plus theta of n over 2. Okay, so that's this thing just substituted. This is my substitution that I've just done. Okay? Just plugging in for n over 2 here means I put n over 2 here and n over 2 here. And then I add in my theta n at the end. And that's equal to 2L of n over 2 minus 1 plus, well, this is twice a theta of n over 2 plus theta n. That's just a bigger theta n. Whatever function is hidden there by the theta n, it's also theta n, it's just bigger. Okay? And what's this? What's the solution to this? This is going to be n log n. Okay? The fact that I subtract 1 here, turns out, doesn't make much difference. It's sort of like a floor or a ceiling. Okay? So this is actually theta of n log n, which is lucky. Lucky wins. It's our lucky day. Okay? Lucky day. Okay? Okay. So this is good, right? Half the time I was unlucky, and yet the times I was lucky, they end up controlling the solution to the recurrence. Okay? And so I get a fast algorithm. So how can I make sure that we're almost always lucky? Or lucky enough, at least a good fraction of the time we're going to be lucky. How can I change the quicksort algorithm?
You could sample to make sure that you're always towards the middle.
Yeah, you could sample to make sure you're getting towards middle. In fact, a very practical implementation of quicksort takes 3 elements and finds the middle element of the 3 and uses that to partition. Okay? And that works pretty well in practice. The problem with that algorithm is that there could be some bad input for which the 3 elements you're picking always ends up having you picking one that's right next to the last one. So maybe I shaved off 2, so I have a 1 to n minus 2 split instead of a 0 to n minus 1 split, but I didn't really didn't chop off a fraction. What's another idea? Yeah.
Pick a random pivot.
Yeah, pick a random pivot. Okay? Pick a random pivot. Okay, that turns out is most likely somewhere in the middle. Sometimes it won't be, but then the next time it's likely to be pretty good. Okay? And that's the basic idea behind randomized quicksort. Which board am I on? This board, right? As I say, this is going to, by the way, we have not hit the hard stuff yet. We're about to. Okay, so, but it's all on the notes are all on the web, so you can do it, and it's also in the book. Pivot around a random element in the subarray. Okay? The nice thing about this particular algorithm is it turns out that the running time then is independent of the input ordering. Because at each point, the pivot element you're picking, it didn't matter what somebody provided as input. You're picking a random element. Okay? And this is important because if you were, for example, in a situation where, suppose you have a piece of code that you want to sell to a customer, and somebody else has a piece of code they want to sell to the customer. The customer says, OK, we're going to run these codes off on each other. OK, you get to look at each other's code. OK, and now you can make up a problem that the other guy has to solve, that both programs have to solve, but in particular, the other guy has to solve. So you sit down with your engineers, right? You figure out what's the really screw case for my adversary, because I want this contract. We've got multi-million dollars, on this one piece of code, okay? So you're motivated to come up with a really bad case. Well, if your algorithm is randomized, he can't come up. Your adversary cannot come up with a bad input, because you're going to be partitioning at random. He's got no control. There's no particular input he can provide that will elicit the worst case behavior. Okay? The worst case is determined only by the random number generator. Okay? And what's good about having it being determined by a random number generator is then we can use mathematics to bound the probability that something bad happens, i.e. it takes a long time. And then we just trust in probability. Now we're going to do simple probability analyses. In the graduate classes, we do what are called high probability analyses. So here we're going to just look at very simple things like expectation. Actually, that's not quite true. We're going to do a couple of proofs that are high probability in this class. But today we're only going to do an expectation proof, okay, showing that the expected time is good. So the analysis is we let t of n. Now t of n is no longer going to be a fixed value. It's now going to be a random variable for the running time. Okay, and we'll assume for this that the random numbers that we generate to choose pivots, and this actually turns out to be an interesting assumption, are independent. And we'll see where that's used in the proof. So that when I partition in one place, that's independent from the element that I pick to pivot in a different place. Those are independent. What do I mean by independent? Everybody remember their 6042 or background in probability or whatever they took? What does independent of two events mean? Yeah.
What I get for this one doesn't affect the next one.
Yeah, or what's the engineering, practical meaning of independence? What do I get to do if things are independent?
Multiply.
You get to multiply the probabilities. Okay, that's what we really care about. Okay, otherwise we can't multiply them. Okay, so this is going to be our random variable t of n. Okay, running time on n elements. And what we're going to do is we're going to define a set of auxiliary random variables. So for k equals 0, 1, up to n minus 1, we'll let x sub k be defined to be 1 if partition generates a k to the n minus k minus 1 split, and 0 otherwise. So as we execute, whenever we generate a split, this random variable is going to be 1 if the split had a balance of k on the left side and n minus k minus 1 on the right side. Okay? And 0 otherwise. What's this type of random variable called? Indicator random variable. Okay? Something everybody, I hope, has some competence with. Because indicator random variables are really neat because they're so simple. Whereas most random variables are really complicated. So if you can bust problems into indicator random variables, it certainly makes the solution easily. One of the basic properties of indicator random variables is that their expectation is equal to the probability that it takes on the value 1. Okay, that's true of all indicator random variables. You just use the definition of expectation. You get 1 times the probability x equals 1 plus 0 times the probability that x equals 0. And that 0 times anything is 0, so you just get the probability it's equal to 1. Okay? And what is that in this case? If I pick the random number, if I pick the partition element at random out of the set of things that I've got to pick, okay, if there are n of them, what is the probability that each of these splits occurs? Any one of those splits occurs. 1 over n. Okay, each element is equally likely to be picked, and whatever element I do, if they're all distinct, that determines what the split is. If I pick the smallest one, it's 0 n minus 1. If I pick the middle one, it's n over 2, approximately n over 2, n minus 1 over 2, n minus 1 over 2. If I pick the largest one, etc. So that's 1 over n. Okay? Okay, so now we can write a formula for the recurrence for the time of n. And first I'm going to write it as a big case statement, and then we'll simplify this case statement a little bit. So the first one is that I'm going to write is that it's t0 plus t of n minus 1 plus theta of n if I get a 0 to n minus 1 split. Okay? So if I get a 0 to n minus 1 split, the random variable is whatever I get on t of 0. We know that's constant, but I'm not going to do that substitution at this point, plus t of n minus 1. I may get a t of 1 plus t of n minus 2 split plus theta n. If I get a 1 to n minus 2 split. And so forth, down to t of n minus 1 plus t of 0 plus theta n if I get an n minus 1 to 0 split. So this basically describes the running time, in terms of the random variable t of n. Okay, describes the running time depending upon what happens. Now this is where the indicator random variables are very helpful, because I have an indicator that tells me which of these things occurs. And so I claim this whole thing is equal to the sum of k equals 0 to n minus 1 of xk times t of k plus t of n minus k minus 1 plus theta n. Oops, I got a parenthesis in the wrong place. Plus theta n. Okay, this is x sub k. Just I didn't write that very clearly. Okay, so the idea here is what's going on? Well, only one of these things occurs. So the indicator random variable tells me which one it occurs, and there it has a value of 1, and I get the value. And for the others, it's 0, so nothing is added into this sum. So that gives me exactly this behavior. So I'm able to reduce a case statement by this clever trick of indicator random variables into a summation. This is really good stuff. Okay, very powerful technique. Okay. So now we can take expectations of both sides, and I can get the expected value. So I get expectation of t of n is equal to the expectation of that thing that I have there. Summation k equals 0 to n minus 1 xk t of k plus t of n minus k minus 1 plus theta of n. Okay? How's that? So let's do some mathematics now. Okay? So the first thing I'm going to do is switch the summation with the expectation. So I'm going to say that's equal to the sum of k equals 0 to n minus 1 expectation of x sub k times t of k plus t of n minus k minus 1 plus theta of n. Okay, why can I do this step? Linearity of expectation. Expectation is linear. The sum of the expectations is the expectation of the sum. Okay, so that's all I've done. Sum of the expectations is equal to the expectation sum. Then I claim that's equal to sum of k equals 0 to n minus 1 of expectation of x, okay, times expectation of t of k plus t of n minus k minus 1 plus theta of n. Okay, what let me do that? Independence, right? You can tell because there's a multiply there. What's independent? Well, what's independent is this particular x sub k in each of these from whatever, and we haven't really named them for in the recursive states, but whatever random numbers are generated in solving the subproblems. Okay, this one is independent of anything in the subproblems. That's what we're using. Okay, because that's our assumption, that when we're picking elements to partition by, we're picking them at random independently every time we do the pick. We don't get to pick one random number and then use it everywhere using the same algorithm based on that number for dividing. Okay, people follow that? Okay, so then that's equal to, now we know what expectation of 1 over x, we know what expectation of x sub k is. I almost gave it away. What is it? 1 over n. So we can pull that out. That's 1 over n sum of expectation of t of k. I'm going to leave off the indices because it's getting 2 times n plus 1 over n sum. Actually, I'm going to leave and put them in. K equals 0 because that's the next step I need it. 0 to n minus 1 of expectation of t of n minus k minus 1 plus 1 of n summation of theta of n. K equals 0 to n minus 1. And what am I using here? Linearity again. Good. Okay. Linearity and the fact that expectation of x is 1 over n. And that is equal to and this is probably the most surprising step. What's that? Why does that happen? No. That's what's surprising. Okay, what happened here?
Well, for the t of n minus k minus 1, there's a or well, it basically does the same thing, but instead it's how
Yeah, these two sums are identical. They're just adding them up. One is going from the bottom up. The other is going from the top down. Okay? They're identical summations, so it's just twice the first one. That's cute. Okay? That's cute. Okay? Now, this is a hairy recurrence. Okay? We're going to simplify it a little bit, and the one we're actually going to solve is expectation of t of n is equal to 2 over n summation of k equals 2 to n minus 1 expectation of t of k plus theta n. That is, I've dropped the k equals 0 and k equal 1 terms. And why can I drop those? Well, those are each going to be terms where I have an expectation of t of 0 or expectation of t of 1, and those are constants. And so therefore, I can take those and put them into the theta n. Okay, and that's a technical convenience for me to do, is to throw those into the theta n, because it'll simplify the math that's coming. Okay? So what we're going to prove is that that expectation of t of n is less than or equal to a n log n for some constant a greater than 0. And the reason I can't do this for n is 0 or 1 is because then this thing is 0. And then it won't be true. But as long as I assume that n is at least 2, okay, then I can do this. And that's why it was convenient to drop those terms and throw them into the theta n here. Okay, because they're just insignificant. In fact, each of those terms is at most theta 1, and we're dividing it by n. So really adding a puny, puny, puny amount to the theta n to make it true. So we want to prove that. How do we prove that? Induction. It's the substitution method. That's what we're going to do. So the first thing is we can choose a large enough to handle any base conditions. Okay, if n is at least 2, then I can always just inflate, for any base conditions, I can inflate a until a is at least big enough to handle any base conditions for the recurrence. So I really only have to deal with the inductive step. And we're going to use a fact. We're almost done here, actually. We're almost done. Which I'm not going to prove, and which I'm going to leave as an exercise. It's not an assigned exercise. in the sense that it's one of the ones, but I encourage people to solve it because it's really a good piece of mathematics to do. Okay, so this is an exercise. What's interesting here is it's easy in the exercise to get the higher order term here. What's hard is to subtract off something. It turns out this is crucial. Okay, this fact that when you sum this, that you actually get something that is less by a quadratic amount from the half n squared log n. Okay, so we're going to use that fact. I'm not going to prove it. And now we just have to substitute. And I find it never hurts to show students more and more examples of induction. So this is our last equation, by the way, and then we're done. So this is less than or equal to 2 over n summation k equals 2 to n minus 1 of a k log k plus theta n. So I told you this would be hard and fast today. Okay, so here we've just substituted into that formula our inductive assumption for values that are less than n, i.e. k between 2 and n minus 1. I mean, this, if you look at the recursion tree, what's going on here is it's really messy, right? Every node has n minus 1 children, but they're all being weighted by this 2 over n factor. So it's really a messy recurrence, no matter how you look about that. We can multiply this through, we can apply this fact. That's less than or equal to 2a over n, because I pulled the a out, times 1/2 n squared log n minus 1/8 n squared plus theta n. Okay, so that's just a little bit of just substituting things in, and we're almost done. That's equal to, now I can multiply through, and I get a n log n, because I multiply this thing through here, and the n over 2's cancel with the 2 over n. Okay, minus, and now I'm going to write it as desired minus the residual. And the residual is, let's see, this term here, which gives me a n over 4, and that term there minus theta of n. Okay. And that's going to be less than or equal to a n log n if I pick a sufficiently large that the a n over 4 dominates the theta n, in which case this whole thing becomes non-negative and the inequality follows. Okay? So I pick, if a is big enough so that a n over 4 dominates whatever function is hidden by the theta n. Okay, so the running time, it turns out, on average, of randomized quicksort is n log n. And in fact, you can show that this not only is the expected running time, but with high probability, you're not likely to see a constant that gets very big either. Okay, but we're not going to show that here. Thank you. Oh, so study groups. People are interested in forming study groups who have time. Why don't you come up to the front here? And people who haven't handed in their homework, please do so. And people can mill over here, maybe over here for the study groups, so that people can find each other.